Welcome to lecture 11. In our last class, we got the voltage across the plate of the capacitor. This expression ultimately it came real, and it should be. Why not? And you see, here is a sine function which is multiplied by an exponential decaying function, and how fast it will decay, it depends upon the product zeta into omega n. Often it is denoted by sigma. Whatever it is, if you sketch this voltage waveform, you will see that the amplitude of this sine function, and then negative of that and plus this constant will give you the voltage waveform like this. You can use MATLAB platform to sketch it for different values of zeta, but mind you, this is the case when zeta lies between 0 to 1, that is less than 1, and characteristic roots, then if zeta is less than 1, is complex conjugate. Then only oscillations will take place. Since the amplitude of the sine wave is modulated by the exponentially decaying function, it will gradually decay, and finally the voltage across the plate of the capacitor will be this E. That's all. So this system is called underdamped system. Underdamped system, because zeta is less than 1. Okay, and if you like, in fact you should do it. You can find out the currents once you have got the solution for voltage. No need of once again solving another differential equation involving current. Simply take C dV dt and also get the current expression as function of time. And only thing, while differentiating, you should remember that product of two functions, time functions, therefore handle them properly, and you can once again get a closed form solution for current, which can be also plotted. And you can verify the boundary condition I0 is 0, and obviously the final current in this circuit is going to be 0 because there is a capacitor present. Final current will be 0. So it is what also to see that what is the waveform of IT looks like against time. That I leave it to you. So this is the thing. But only thing, while sketching this waveform, you should note that this is Bt. So it should be like this. This portion students often draw like this. This is wrong. Yes, dBdt must be 0. Then only I will be 0. So it will come like this and so on. Now there may be other two situations when the roots are not complex. So I will just point out those things. For example, you say the characteristic roots of this equation is minus zeta omega n plus minus root over zeta square minus 1 into omega n. So that was the case 1. When zeta was less than 1, this term became complex, imaginary. And now I am saying another case could be case 2, say case 2. I don't remember in my note whether it was case 2. Anyway, that is not very important. So case 2 is, suppose I say zeta is greater than 1. If zeta number is greater than 1, then the roots will be real. Then roots will be real. So the algebra which will follow will not be so much involved as it happened in case of complex roots. Therefore M1 will be equal to minus zeta omega n. One root will be plus of root over zeta square minus 1 into omega n, and m2 will be equal to minus zeta omega n minus root over zeta square minus 1 into omega n. So both the roots will be real and distinct. Real and distinct. They are different, not repeating. So roots will be distinct. Then the solution I will simply write Vt is equal to, I am not going to do it, e to the power m1t plus a2 into e to the power minus m2t, is not, and plus the solution due to forcing function. That will be there. m1, m2 are these numbers. Mind you, both these roots will be negative, because this is zeta, this number is positive under root this, so negative, 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 and this number is positive, no doubt, but it is less than the negative value zeta omega n, because you are subtracting one then taking this. So both roots are negative also, that must be noted, but the time constant involved may be different. But anyway, so this will be the waveform, and this case is called, and there will be no oscillations, no j omega t terms are there. So it is a real function of time, and the sketch of this waveform will be like exponentially, I'm sorry, m2t here, and it will be somewhat like this. If you add these two exponential, ultimately it will look like, and such a system is called overdamped system. Overdamped system. Okay, that is, resistance is value is much higher, so no oscillations will take place in this particular case. Similarly, there may be a situation, and the third one is what is called this is the expression of the root. I look at this equation. The case 3 is if what happens if zeta equal to 1, RLC values are such that zeta becomes equal to 1, RL values are such. So if zeta happens to be equal to 1, then roots will be equal, real and equal roots. Both the roots will be minus zeta omega n, and then the solution Vt will be equal to, the transient part of it will be, we know it will be a1 plus a2 into t, is not, into e to the power minus zeta omega n into t, and of course the solution due to forcing function, which will remain as e. Therefore, this a1, a2 in both the cases, case 3 and case 2, here also you can find out a1, a2 values by putting the boundary condition I0 is equal to 0. This time you will get real algebraic equations, and V0 is equal to 0. You can get that, that I have found out in my notes. You can go through it, or any other book you consult. It is your preference. But that note I will, most probably I have uploaded, I will do that. Similarly here also A1, A2 to be found out from the condition I0, because same stuff I am not repeating. I have done for the difficult part, that is the complex conjugate, where we learned about this constant should be complex conjugate. Those are important informations which you should not forget. Here it will be just algebraic real quantities. So in essence, it is the value of zeta. For example, when the roots will be complex, zeta lies between 0 to 1. And if you make zeta further less, so this is for one value of zeta, say zeta is equal to 0.5. Now you can say I will decrease zeta. Zeta means you are reducing resistance. Then the peak value of this one will be higher, and you will be getting much more. I am just roughly sketching. This need not be the exact thing which you will plot. So more oscillations will take place with larger amplitude. So these are the example. Further make zeta less, peaker the waveform will become capacitor voltage. Oscillations will be much more. It may take longer time to die down, and of course eventually it has to come to capital E only. That should be understood. In case of these two, this case, when the roots are real and equal, and of course negative roots, then it is called, system is said to be critically damped. Critically damped. Its response will also look like exponentially growing. If this is your E level, if this is t equal to 0, it will go there like this, critically damped. Two exponential functions adding. Mind you, this second term, it looks like it is multiplied with t. As t grows, this goes on increasing linearly. But this fellow, multiplied by e to the power minus zeta omega n, pull it down back to 0 as t goes to infinity. So it will be more or less like this. You can sketch this function as well under this condition. So critically damped case and over damped case, I just now told you it is over damped case. It will be taking much longer time. So in a waveform, just roughly I am sketching, not to the scale or anything. It looks like the response, that is the capacitor voltage, suppose, it will be something like this. It could be against time, this is E. It could be under damped case, when the roots are complex conjugate. Zeta is less than 1, 0 to 1 it lies, so this is under damped. Okay, then you can have critically damped. You can have critically damped. Oh my God, it is not right. Critically damped. When the roots will be equal, critically damped. And finally, it could be a overdamped system as well. It could be overdamped system as well, like this. Of course, at t equal to 0, they must satisfy dV/dt slope should be 0 in all these cases, because current has to be 0. And so it will have a bend like this and then grow up. So these are the three situations with which the capacitor voltage will finally build up. This can be also we experience in our everyday life. In your mechanical system, a very nice example of this is your swing door. Okay, on the door you connect a some arrangement there where the door is the mass, then there will be a spring, and there will be friction or damper they call it, which takes place of the resistance. You try to open the door, you push it and release your hand. That means you have given some energy into the system, and see what the door is doing. If it is a underdamped case, then the door will swing like this, plus minus plus minus. Finally, eventually it will come to zero. And that is of course not a very good design for the swing door, is not? And if it is suppose the resistance or damper present in that module of the swing door, which is attached on the top of the door, you look at it, and if it is resistance or dampers, where friction is very large, then you give it, it will go to the steady state slowly without any oscillations. Got the point? And if it is critically damped, it will go also exponentially slowly, perhaps it will take less time. Generally, while designing such systems, you make it slightly underdamped, so that it goes, it may have one or two oscillations before it final positions. I'm telling, it may be like this. Anyway, you think of yourself of any other system. So in RLC circuit, resistive element is there, L and C energy storing elements is there, and when you switched it on to a DC supply, I know several things before I solve it. First thing I know is that since resistance is present, finally the fate of the capacitor voltage will be the supply voltage itself, because whatever energy are oscillating, that will gradually dissipated in R. Second thing is final current in the circuit will be zero, and in all these three cases you try to somehow get Vt and then differentiate it and multiply with C, get the current waveform, and also we know final current waveform is zero. So no matter whether it is a overdamped system, underdamped system, or critically damped system, final voltage of the capacitor has to be that battery voltage. Final current has to be zero. But the way it will reach to those final states is decided by the positions of the characteristic roots, whether they are complex conjugate, whether they are real and equal, and whether they are real, negative, and not equal. So you please go through those things. So in the laboratory, when you carry out this experiment RLC excited with a DC voltage, what you should do, you make the circuit like this. This is initial conditions are all 0. Close the switch here at t equal to 0. Connect an oscilloscope probe across capacitor voltage to see how this voltage changes. Choose some value of RLC. If R value is pretty small, in fact, zeta expression. So relative to whatever factor is there, you choose very little R value, there will be more oscillations in the circuit before the capacitor voltage become ET, and it will be like this somewhat. Capacitor voltage. Similarly, current waveform can be seen because the resistance is a memoryless device. So you also see the waveform across R. That will in fact will be the current waveform of the circuit, because V equal to IR. R is constant number. Choose across the same R. If you see the voltage waveform across R and voltage across the capacitor, you get both the voltage and current waveform. You imagine R has been very large, suppose R is very large, such that it will become an overdamped system. That waveform also you can see capacitor voltage and the current in the circuit. And look at these equations to make it a critically damped system, that is zeta is equal to 1. What should be the value of R chosen? LC, if you have already chosen, you can select the value of R and connect that value of R, LC, then also you will see the voltage and current waveform. Now, so the experiment part is very straightforward. I will excite this with a battery voltage, and I would like to see how the capacitor voltage looks like. From there, perhaps I will, because digital storage capacitor, you can do many things. You can measure this time period, omega d, and whatever RLC you have calculated, you compare with this time period with 2 pi by omega d from your circuit theoretically, whether it is matching or not. Those are very interesting observations. See the time constant, how fast it reaches the steady state value E. So those are details as listed in the experiment number 2. So go through please that. So I am stopping here now, and because the steps are more or less similar, and for case 2 and case 3, go through them. Go through also the manual of your circuit in the first part of the experiment, RLC circuit response with that. And don't confuse it with the RLC circuit experiment that you have performed in your first year ET laboratory. There also it was RLC, but it was excited by some sinusoidal voltage, and only the steady state current you were examining. Got the point? There is no question of circuit reaching a constant voltage. No. So that's all for the time being, and I will tell about the experiment 2 in my next lecture, a small part of the experiment, and then I will give you upload the problems that you have to solve, whatever I have told you in this class. But mind you, in spite of my lectures, you consult books, that is good, because I really not sure while doing whether did I make any basic mistake or not. You please go through this, and it will be very nice if I get your feedback so that I can correct those. Also, I'll be very happy that if some mistake or conceptually or otherwise, you can point that out to me through emails or things like that. But in any case, I think you have got a fair idea what you are supposed to do. So experiment 2, second part, I will come up in the next lecture. It is a small lecture. Thank you.